The next major topic I want to discuss is the OSI model. The OSI model stands for Open Systems Interconnect Reference Model. The OSI model was created initially as a reference model and teaching aid to help students and other people learn how protocols and networks all work together to carry out the job of moving data from one end to the other of the network. It was never intended to actually reflect any actual networking architectures. Aside from being a device to teach people how protocols and networks work together, the OSI model was also a model that was intended as a reference for organizations to use when creating new protocols. By using the model to create new protocols, organizations could be assured that the new protocols that they created would fit into an overall architecture without having to basically reinvent the wheel each time they did it. The OSI model looks like this. The OSI model has 7 layers, and each one of these layers has a unique specific job, which we'll get into in more detail in following videos. Now, starting at top to bottom, we have the application, presentation, session, transport, network, datalink, and physical layers. A way to memorize these layers in the proper order is to use a mnemonic. A mnemonic is a memory device that helps you learn each layer by using a word or a common word that is the first character of the layer that you're trying to memorize. So, a mnemonic commonly used to learn the OSI model from top to bottom is this: all people seem to need data processing. Another mnemonic that is commonly used to learn the layers of the OSI model from bottom to top is please do not throw sausage pizza away. Either one of these mnemonics or one you create for yourself will help you memorize the proper order that the layers of the OSI model should be in. The OSI model, when it was first created, came out in 2 parts. The first part was the abstract model that we just looked at. This model had the 7 layers as we've just discussed it. The second part of the OSI model was actually a specifically created set of protocols that was designed to illustrate how the protocols would fit inside this abstract model that was created to help teach how networking and protocols work together. The protocols that were created are not actually used in any network systems and were not really intended to be used in network systems. They were strictly intended to be reference protocols that other people could use to create protocols in the future. 2 organizations published the OSI model back in 1984. One of the organizations that helped publish the model was the International Standards Organization. The International Standards Organization published the model as the ISO 7498 standard. The other organization that helped publish the OSI model was the Telecommunications Standardization Sector of the International Telecommunications Union, or ITU-T. ITU-T published the OSI model under the ITU-T standard X.200. A good place to get additional information on the OSI model is this website right here that is part of Microsoft's support webpage. Now we've talked generally about the OSI model, let's go ahead and talk about the specific layers of the OSI model. First, I'd like to talk about layer 1, or the physical layer of the OSI model. The physical layer of the OSI model is the bottom layer, and is concerned with the physical transmission of raw data across a network. This data is transmitted in the form of ones and zeros, otherwise known as digital transmission. In order to define the digital transmission, the physical layer also has to define the encoding method used to transmit the ones and zeros. In order to define the method to encode the ones and zeros, the physical layer has to also define how the bits are placed on the media, and it defines different ways to place bits on different media depending on the type of media being used. Finally, the physical layer, when it comes to defining how data is encoded onto the media, also has to define how bits start and stop. Otherwise, you'll not have a clear distinction between each bit that's transmitted across the physical medium. Beyond defining how data is encoded onto a physical medium, the physical layer also defines specifications that relate to the media that's being used. When the physical layer defines the media being used, it's basically saying what kinds of media are permitted for different devices and what kinds of media are not permitted. Beyond defining the types of media that are permitted, the physical layer also defines how the physical connections are made with those media. This is done by defining pin usage and other types of specification that apply to the physical media that's being used. Defining pin usage would apply to copper type media, but if you're using wireless type media, then the physical layer would define how the waves are modulated or the frequency of the waves that are allowed to be used. So these are the kind of things that the physical layer defines when it's putting specifications on the media usage that the physical layer is using. One thing to keep in mind, when the physical layer specifies a standard, that standard only applies to a very specific type of media. Different types of media, even different types of copper media, are going to have different standards that are specified by the physical layer. The next layer we want to look at is layer 2, or the Datalink layer. The Datalink layer provides error-free transmission from one node to the next over the physical media. The Datalink layer does this by establishing and terminating links between adjacent nodes. By being responsible for establishing and terminating links, this means the Datalink layer is also responsible for a certain measure of traffic control. Part of that traffic control is to verify that frames are transmitted and received in the correct sequence. Also, the Datalink layer is responsible for frame acknowledgement. The Datalink layer, when it transmits a frame, expects acknowledgement to be sent to it. By the same token, when the Datalink layer receives a frame, it in turn provides acknowledgement back to the node that sent the frame in the first place. The Datalink layer is also able to detect and recover from errors on the physical layer of the OSI model. One of the ways it can recover from physical errors is by retransmitting frames that it didn't get an acknowledgement for. Also, the Datalink layer can handle duplicate frame receipt. In other words, if a node was sent 2 frames that are exactly the same thing, the Datalink layer can eliminate one of the frames, thereby preventing problems further down the line. Beyond recovering from errors and other types of things, the Datalink layer also is responsible for frame delimiting. What this means is that the Datalink layer is responsible for creating and recognizing frame boundaries. Or, put another way, the Datalink layer is responsible for indicating when a frame starts and when a frame stops, so that the nodes that receive the frame will know the boundaries of the frame that it is receiving. Beyond recovering from errors on the physical layer, the Datalink layer also is responsible for error checking. The way the Datalink layer does error checking is it checks the frames it receives and makes sure that the data inside the frame hasn't been altered or modified. This is called checking for data integrity. The Datalink layer also provides media access management. What this means is the Datalink layer determines when a node is allowed to use a physical media and when it's not. This helps prevent frames from hitting each other or from frames being cut short before they're fully transmitted, thus minimizing or eliminating a lot of errors in the transmission process. Layer 3, or the network layer, is the layer I would like to talk about next. The network layer controls the operation of the subnetwork it is located on. Part of controlling the operations of the subnetwork it is located on is determining the best physical path for data to take in order to reach its destination. The network layer can use several different metrics to do this. One such metric is the condition of the chosen path. In other words, the network layer is able to look at conditions on the network such as congestion, whether a node is down, whether there's a lot of traffic, things like that, to help determine or help choose the best path that a data packet can take to get to where it needs to go. Another way that the network layer can determine the best path is to look at the priority given to different paths on the network. And then based on the priority, the network layer is then able to choose which path works best for a given packet. Finally, the network layer is able to use other factors as well. Some examples of other factors that it may use to determine the best path would be things like the number of hops or the number of steps between the source and destination. It also may look at bandwidth or throughput, or it may look at the different types of technologies needed to get from one place to the other. It can compare all these pieces of information and put it all together to determine the best path for a particular packet to follow. There are several functions that are provided by the network layer. One is the aforementioned routing. Basically, what it does is it routes frames among the connected networks along the best path needed to get to the destination. Subnet traffic control is another function of the network layer. Basically, when we talk about subnet traffic control, what we're saying is the network layer allows routers to send instructions to each other based on what's ever going on with the routers. For example, if a router is receiving too many transmissions to the point that its buffer is getting filled up, then that router is allowed to send out a message telling the router sending the information to throttle back or to slow down because the buffers are getting overloaded. There are many other similar type commands or instructions that routers can send to each other on the network layer to make sure that the traffic control on the subnet is running at an optimum rate. Frame fragmentation is another function of the network layer. Now, when we talk about frame fragmentation, what we mean is that the network layer determines the size of the frame that routers downstream are using to transmit data. It then takes that frame size, which is called the maximum transmission unit, and then if necessary, it breaks up the data that it wants to send into a size that matches the MTU, or the maximum transmission unit size, of the routers that it's going to be passing through downstream. Also, if the frame does need to be fragmented or made into smaller frames based on the maximum transmission unit, then the network layer is also responsible for reassembling the frames into the full frame size at the destination. Logical physical address mapping is another function of the network layer. Basically, what this means is the network layer translates logical addresses into physical addresses. We'll be talking more about logical and physical addresses at a later time. Finally, we've got subnet usage accounting. Basically, subnet usage accounting is the function that allows the network layer to keep track of frames as they're forwarded by a specific subnet intermediate system. By keeping track of the frames that are forwarded by each intermediate system, the network layer is able to use this to produce billing information that can in turn be handed over to a company to charge them for data usage or bandwidth or something like that. Much like what your cellular provider will do when it comes to how much internet you're allowed to have each month. Part of the reason the network layer is able to do all these things is because it builds specialized headers that are used by the network layer on other devices in order to route packets safely and correctly to the destination they're trying to go to. These headers that are created by the network layer relieve higher layers of the OSI model from having to know anything about the data transmission or the switching technologies that are being used on the network. That becomes the job of the network layer, and the higher level layers can then spend their time and effort doing whatever it is they are intended to do. Also, the network layer is able to use protocols on the lower layers to send data to destinations separated by multiple intermediate nodes. The way data is sent to multiple intermediate nodes is by basically sending the data from one node to an adjacent node, which then sends the data from that node to another adjacent node, and so on and so forth till it gets to the destination. This is also something that we'll look at in more detail later.